I just made sure that you had a copy. So we are meeting again after 1 month pause. I hope everyone had a pleasant holidays and Christmas, New Year's. Winter has arrived here in Canada, so up until before Christmas it was quite nice, but now it's been really quite cold the last few days.
Do you have snow?
Oh yes, lots, quite a lot. Actually, well, it does. It's still in that mode where it melts one day and then goes to 20 below Celsius the next day. That sort of thing where the variations are very large. But it's definitely feels like winter, and we have to deal with the kind of winter effects that we have since we live out in the country anyway. So it's takes a little longer to get things done.
At least you have electricity.
Absolutely, yes. That makes a big difference. And we have internet, so we're not alone. Yeah, so I guess no one else is going to show up, so we'll just sort of start with our informal program. Our proposal that I discussed with Dr. Santilli and Dr. Sobczyk was that we would informally discuss the draft paper that Dr. Santilli sent about a week ago now, I think. But also, Dr. Santilli suggested that we could start with an emphasis on quantum mechanics, or specifically hidden variables, and David Bohm's views about quantum mechanics. And that would be my part. But we wanted to limit that. It's a very big subject, so you could easily talk a long time. So I've sort of had some, I don't know, I haven't had much time to prepare, but I've been thinking about David Bohm's quantum mechanics for quite a few years now, probably 30 years, mostly in conjunction with meetings similar to this, in fact, that I have with my colleague David Sagansky. I think David introduced himself early on, like maybe in September or October. At one of our meetings he did show up, but he's otherwise rather busy, but mostly because he's now in retirement and doing a lot of other things. So like all of us, once you get into retirement, you no longer have time to do anything. You're busy with everything. Whereas when you're busy working, then you always manage, for at least in my case, I always manage to make time for physics. But now when my own other priorities interfere with that, then it seems much harder for some reason. I don't know. But anyway, he and I have been discussing David Bohm for many years, and still are very actively discussing it. So what I thought I would do is sort of give a discussion of what is quantum mechanics, and what were David Bohm's views about quantum mechanics, but from a more modern perspective. Like David Bohm published in the 1950s, and then later published a book, I think about I don't know, early 1980s. But my primary reference would be a book written by a student of David Bohm's named Peter Holland. Peter Holland was a PhD student with David Bohm. And I think it was just shortly after David Bohm died in the 90s, Peter Holland published a book called Quantum Theory of Motion. That one's been on my desk almost all the time for the last 30 years or so. I'll send you a link to that. Let's see. So let me just put this in the chat window. Chat. Yeah, so that's a link to the Cambridge book site. This was published by Cambridge Press in. Oh, and there's an online version too now. I didn't realize that. It was originally published in 1993.
What's the author's name again?
Sorry?
What is the author's name again?
Peter Holland.
Oh, Holland, okay.
Yeah.
Okay.
Yeah, so he wrote an entire book, and his goal was to summarize David Bohm's views on quantum mechanics. Holland is still very actively publishing, but he has moved on a certain amount. Let me give you a reference to a more recent paper by Holland. What is that one called? Oh, here. Yes. Just so we have the same references here. Here's an archive link, for example, of a paper published in November of last year. And this one is called bi-Hamiltonian bi-Hamiltonian Jacobi theory of quantum evolution. And it's the most recent of a series of papers that he's been doing. David Bohm, Holland now views David Bohm's ideas on trajectories in quantum mechanics as, say, the first part of a three-part story. And about 2 years ago, he published a paper with alternate definitions of trajectories that he called a two-fluid model of quantum mechanics. Quantum mechanics has often been considered from the point of view of fluid dynamics. Probably just shortly after Schrödinger published his first paper, an author named Madelung pointed out that the Schrödinger equation can be viewed as an Euler equation for a fluid that one would usually think of as representing the probability, but the probability density moves like a fluid in fluid dynamics with a particular type of particular dynamics that is unique to quantum mechanics, but still it looks like a fluid. And this, so that was Holland's second picture, was to point out that one could get rid of the notion of quantum phase altogether, and deal with a pair of real valued equations with a pair of real valued density equations. So you consider a system in which there are two densities that interact with each other, and that the interaction of the two densities is what gives rise to quantum mechanics. It is exactly equivalent to the Schrödinger equation. And then in this most recent paper, Holland shows that, maybe I should back up a little bit. In the original David Bohm views of trajectories, the trajectories were described by an equation that looked very much like the Hamilton-Jacobi equation in classical mechanics, classical statistical mechanics. And that the motion of particles in David Bohm's theory is determined by this quantum mechanical Hamilton-Jacobi, and the evolution of the density is determined by the usual continuity equation that describes the conservation of probability. So one can view Holland's second picture, that is in terms of two fluids, as being a picture entirely in terms of continuity equations between two fluids. And now his third paper, it sort of returns to the original idea that, or to the other idea that was embedded in Holland, in David Bohm's view, and that was the Hamilton-Jacobi. And so in this third paper, the most recent paper, he shows that the Schrödinger equation can be viewed as a pair of Hamilton-Jacobi equations, completely eliminating the concept of density altogether, and dealing with the quantum state only in terms of the motions of two different types of particles described by the Hamilton-Jacobi. So anyway, so that's Holland, and I think his view of David Bohm is probably the best and the most up to date. But one of the things that I wanted to emphasize is that Holland, and more recently another author, another group of authors, have pointed out that one can view Schrödinger's equation as being derived directly from classical mechanics, from classical statistical mechanics. And let me give you a reference to this article, because this is the article that my friend David Sagansky and I are discussing at the moment. And we have rather different views of the meaning of this article. And in this case, I'm defending the conventional classical view of statistical mechanics, whereas David Sagansky, my colleague, views this paper by Sletch as being sort of a little bit misguided in thinking that one can take classical mechanics and treat it or see directly from classical statistical mechanics, see how Schrödinger's equation arises. But
I have a quick question. What is,
sure.
So in these other ways of looking at it, how does the hidden variable idea arise, or where does that come from?
Yes. Okay. I should answer that quickly, but then I would back up and give it a better answer later. But in David Bohm's quantum mechanics, the thing that is hidden is the wave function. The thing that we observe is the particle. So the dynamics of the particle motion in David Bohm's theory is determined by something called the guidance relation, which relates the velocity field of the particle to the phase of the wave function. Now, the reason why the people think that Schrödinger's equation should be able to come directly from classical mechanics is that exactly the same thing happens in classical statistical mechanics when you view it from the point of view of Hamilton-Jacobi. So if you look at Hamilton-Jacobi, you get a pair of equations. One that tells you how a scalar field, usually denoted by S, this function varies over time, and then the derivative of s with respect to the position is exactly equivalent to momentum. And the derivative with respect to time is exactly equivalent to the total energy. But if you take the derivative with respect to the position and divide by the mass, then you have an expression for the velocity field. And that same expression for the velocity field that works in Hamilton-Jacobi classical case is exactly the same thing as David Bohm's guidance equation, right? That relates the motion of a particle that's following David Bohm's trajectory follows exactly the path that's determined by the quantum Hamilton-Jacobi equation, using the same approach as in classical mechanics. So the particle is what one observes, is what's real. What's hidden is the basically the dynamics that's embedded in the wave function. So David Bohm's theory takes both the wave function and the particle as both being real, both representing ontological, like reality, and that the wave function determines the motion of the particle. And then things like the two-slit experiment and things like entanglement or non-local relationships between entangled particles that have been widely separated are expressed in almost a pure quantum mechanical way through the dynamics expressed by the Schrödinger equation of the wave function, or more particularly of the phase of the wave function. So the reasons why two widely separated particles interact is expressed in David Bohm's approach just by accepting the reality of the wave function, even though we don't actually have a way to directly measure the wave function. So he wants to take the wave function as a real field. And this actually is not so different than what Schrödinger started with. Like when Schrödinger first wrote down what we now call Schrödinger's wave equation, Schrödinger also was thinking of the wave function as somehow representing physical reality.
Yeah, if I may have a very quick comment. Personally, I'm 100% in agreement with what you indicated. Indeed, what we have called, the EPR entanglement is centrally dependent on admitting the wave function as being physical, and indeed the entanglement is assumed to originate precisely in the interaction of wave function. So also we're completely in agreement.
But this does represent, it represents a significant challenge still. I mean, accepting the wave function as a real field leads to a lot of conceptual difficulties from
mathematical.
And there is a solution, I think, that, I mean, I would want to propose that there is a very easy to understand solution that actually comes from this description of quantum mechanics arising from classical statistical mechanics. There's a way to see what's different and what's implied by quantum mechanics that's not implied by classical mechanics. But you have to start first of all with classical mechanics, since that's the type of system about which we have the greatest intuition.
Yeah, we're fully in agreement on that point as well.
So let's see, where are we going? How far have I got? I've probably spent too much time already. So this paper by Sletch, Greenberger, Kolbe, and Scully, all of which are very highly regarded physicists in the U.S., basically are supporting the views that were presented, in fact, earlier by Holland. In chapter 2 of Holland, Holland presents almost exactly the same argument as these people here. And oddly enough, neither of them reference each other. They're sort of independent of each other. Let me give you one, since I have it here on my screen, I'll give you one more really good reference. Yeah, so where is this one? This one here. This is another recent paper, but published by lesser known authors. But these authors take the view that if Schrödinger was alive today, and he had the kind of background that people have in mathematics today, he probably would have done what he did in 1927 in a slightly different way. In fact, that way of doing it is exactly the way that Peter Holland presented, and in the same way as Schlesinger
I understand that Schrödinger actually invented matrices, basically linear.
No, Schrödinger invented.
Or was it Heisenberg? I guess it was Heisenberg.
That's Heisenberg is the one who views things in terms of operators, right? Matrices are one particular representation of operators. But when we talk about the Heisenberg picture of quantum mechanics these days, we're really talking about operators. And what Heisenberg did originally was just to represent operators by matrices and so forth. But it's long been known that this is the equivalent, that both Schrödinger's and Heisenberg's views are equivalent, mathematically speaking, though they do give somewhat different views of how to present the dynamics. And one picture is more convenient for certain types of calculations than the other, but in the end, they both produce the same result, completely consistent with each other. What Holland is doing, though, is showing that there are other completely different pictures. And Holland presented 3 different pictures alone that dealt just with trajectories, whereas the original pictures of Heisenberg and Schrödinger had nothing to do with trajectories directly. But the fact that trajectories were missing in quantum mechanics, and even still, are hard to understand in quantum mechanics, is one of the things that leads to conceptual difficulties. You have to, one of the things that happened in the early days of quantum mechanics was that Bohr in Copenhagen and so forth basically gave up the idea that one would understand mechanics beneath quantum mechanics, and took a completely positivistic view that said that the only thing we can explain are measurements, and that this was actually the origin of the debate with Einstein. Was that Einstein insisted that he wanted to understand the mechanism behind quantum mechanics, and as soon as you do that, then you lead directly to the EPR paradox. EPR was a paper published by Einstein and Rosen-Podolsky, but Einstein actually started that discussion a few years earlier, directly with Bohr, and apparently Einstein even came up with a solution that provided a mechanics, but then at the last minute withdrew that paper because he was arguing with Bohr, and Bohr was saying something like, well, there is no mechanics behind quantum mechanics, really. It wasn't called quantum mechanics then. He was arguing that what you have to do is just take a completely abstract view, that what we're able to do in physics is to compare some measurements to other measurements, and these measurements are almost always of a probabilistic nature. There are no exact quantities. And so he just embraced the idea that there was this uncertainty relationship as sort of central to quantum mechanics. But Einstein didn't appreciate that at all, especially when it was shown in this EPR paper that if you took a view of, say, two particles interacting as a system, then there were states of these two particles in which we view the two particles as separating, as being, many light years apart. And then the measurement on one of these particles immediately determines the value of the measurement that one would get from the other particle, even though it's many light years away. Like so this was the heart of the EPR argument, was that how could this possibly be, since it obviously conflicted with relativity, since there was no possible way to send a signal. There's no type of interaction that we know of that could relate a measurement many light years apart. But yet quantum mechanics predicts that as a direct outcome of quantum mechanics. And,
well, then, if I may, I appreciate the elaborate a little bit, Dr. Page, on the prediction, because there are objections against the very name of quantum entanglement. This was during the Einstein time, because quantum mechanics cannot represent, there is no way for that I know. I'm referring to the word quantum mechanics may be highly misleading. I am referring specifically to the Copenhagen interpretation of quantum mechanics. There is absolutely no way whatsoever that is a local theory can not represent.
Yeah, that's the key issue.
So the prediction.
Well, you just raised a very important word that I didn't use yet, and that is local, right? So the way that David Bohm's theory or interpretation of quantum mechanics gets around that is accepting non-locality, basically.
Yes, that's why.
Basically yes. Says non-locality exists in nature, and yes. You should just get over it, right? Like that's what's implicit in the Schrödinger equation, and you can do this without actually destroying relativity, but you have to do
yes.
it in a very subtle way. Right?
Yeah, sorry, but it means. I mean to interject quickly, but that's the very reason why we consider David Bohm a founder of hadronic mechanics, because he's founded precisely in those ideas. We only find the ideas are David. Only we find a mathematical representation via the isotopic element, a quantitative representation in agreement with experimental data. That was missing, but yeah, basic idea.
But still, well, this is where I start to be perhaps a bit skeptical of at least the introductory part of your paper, and the key part of my objection is the idea of being able to deform a charged cloud, right? Like you think of this, like one of the issues in quantum mechanics is that the charge density is closely related to the density as expressed by the wave function, and this basically the absolute value of the wave function squared is the density, is the charge density. But when you interact with this charge density, you don't interact with the density as you would, like, say, a cloud in the atmosphere, or like a water droplet. Like so it has a density. One water droplet interacting with another water droplet has very different dynamics than if you shoot one electron at another. So when you look at what happens when you shoot one electron at another, it's as if the electron rebounds off of something, even though the something itself is a cloud, right? It's somehow distributed over space. But when the interaction occurs, when we actually make a measurement, we see that the electron actually hit something in the cloud and went off. It didn't actually just sort of deform the cloud a little bit and move off, right?
Yeah, but those are beautiful idea, but there is no known quantitative representation via equation, especially for electrons.
This is where I would disagree. But in order to
But perhaps we can discuss this after my let's review on my part.
Yeah,
and
sure.
then perhaps we can discuss more and more significantly. The main is to separate conceptual beautiful conceptual view from quantitative representation of experimental numbers. That's what the main objective is. So perhaps we can discuss it after we
Yeah. I just want to raise one more issue before I sort of release the.
Please, any criticism is welcome.
And that is that well, let me look. I have one more little thing to show you, and I hope it doesn't take too long. So this is calculations done in Maple, and it was part of the kind of dialogue that my colleague David and I have about quantum mechanics. So we are discussing this paper by Schletch, Schrödinger equation revisited, and David made some claims that he felt that this paper wasn't doing a good job of the argument, and so basically we started by discussing what does it mean classically, like so this Hamilton-Jacobi equation here, as I said, contains a field called S, which is the phase of the wave function, and these are classical equations, and there are two equations, a pair of equations, this Hamilton-Jacobi equation, and then the associated continuity equation that describe how the density changes, but there's one of these determines the other, but so that, or at least is involved in the other, is dependent on the other, so that S appears in the density equation, but the density does not appear in
Dr. Page, allow me to...
And that's completely different in quantum mechanics. In quantum mechanics, you still have two equations, but the density affects the dynamics, whereas in classical mechanics, the density does not affect dynamics. But ultimately,
it's a beautiful formulation, which I agree fully. I only want to clarify one point, that Jacobi, like Hamilton and Lagrange, they included in their analytic formulation external terms. So therefore, those equations that you show are outside the class of unitary equivalents of what is historically, technically known as quantum mechanics. It's a beautiful formulation, but to my knowledge, you are outside quantum mechanics. Incidentally, I agree fully because I agree fully with the content, with the equations, because this is slightly on this point. So, but however, let's clarify, this is not quantum mechanics, no connection that I know. Is a non-unitary transformation of quantum mechanics.
This is classical mechanics. Yes, this is classical mechanics.
Yeah, but there's a foundation you mentioned, then later on, the operator form of, whenever you mention Jacobi, is meaning mentioning analytic mechanics, mentioning external terms, especially for you cannot formulate a consistent equation for a density function, a density for any density, unless you have external terms, because in the fluid dynamics you have contact interaction, which are not derivable from a potential.
So here we're not dealing with contact interactions at all.
I know, but they are implicitly, yes, I know, but they are implicitly included in the equations. In other words, you quantize those equations, you don't get shredding. You get shredding, you get the completion of
no. This is where you have to look very carefully at what this paper.
I will. Oh yes,
right?
I will.
This paper presents this equation number 2 here is a classical Schrödinger equation. It's quantization applied to classical mechanics, classical statistical mechanics. And the surprising thing that happens is that when you write out the wave equation, the same wave equation that you would write out for Schrödinger, but if you do the same thing, if you start with classical statistical mechanics, you get a wave equation that includes a nonlinear term.
Yes.
But
yes.
The whole point of this nonlinear term is to enforce classicality. Right?
Yes, I agree fully.
And,
I agree fully.
and if you remove this linear term, if you ignore
Non-linear
that
term.
linear term, then you get exactly Schrodinger's equation.
Yes, yes. This is
Right?
also
So basically you've just said quantum mechanics is the same as classical mechanics, but we forced it to be linear.
yes, yes,
Now,
absolutely.
as soon as
true.
we
Very,
force
very
it to
true.
be linear, though,
Very true.
right? As soon as we force it to be linear, this term doesn't go away, though. Right? The thing is that this term moves from being part of the wave equation into being part of the Hamilton-Jacobi equation.
Yes, yes, indeed.
So
Yes.
that the Hamilton-Jacobi equation is extended to be quantum mechanical Hamilton-Jacobi. And when you do that,
Non-linear.
and if you look at the meaning of this quantum Hamilton-Jacobi, these solutions to this equation are exactly Bohm's trajectories. That's
yes,
the point.
yes,
right?
I agree fully.
Right?
I agree fully.
So and the weirdest thing here, the first thing that's hard to accept, and the reason why it wasn't done this way until I think it was about 1960 or so, I forget. This paper does point out who the original authors of this idea that you could write classical mechanics using a wave equation. It wasn't done earlier on, like it wasn't done in the 1900s because there wouldn't have been any point. Plus, there wasn't any physical motivation for this nonlinear term. Like this nonlinear term looks unnatural, and oddly enough, it introduces Planck's constant right at the beginning in classical mechanics. So we need Planck's constant in order to describe this nonlinear term. In order to write classical mechanics as a wave equation, you have to introduce Planck's constant anyway. So the thing with quantum mechanics was that it said, well, we don't want this complicated wave function. We want the wave function to be linear, right? Because as soon as we can make the wave function linear, then we have a whole lot of mathematics that we can do. But the cost of doing that is to add this same term, this quantum term, to the Hamilton-Jacobi, and this term is where the non-locality enters. That this makes the quantum Hamilton-Jacobi into a non-local description of motion. So using the quantum Hamilton-Jacobi equation, it's easy to see how something that's widely separated interact, because there's this additional term in the quantum Hamilton-Jacobi that describes that specifically, that interaction.
Can I make one question? Why by adding one term does it make it linear? Or how is it not linear if you don't add the term? It's
Okay,
linear.
well, like this term Q is nonlinear in
the wave function.
In the wave function, yeah.
Yeah.
I don't have the
Okay, so
expression is here.
So how does that make it? Yeah, I don't understand why it makes it linear.
When you remove the equation depends on the remains. It depends on the first power, zero power of the wave function. Namely, it depends on the wave function at the first power, if you want. But the nature is expected to depend on the power of the wave function. That's Heisenberg. Heisenberg, incidentally, Dr. Page Heisenberg wrote a beautiful book on the non-linear extension, if you want. We use the word completion of quantum mechanics. And I think this equation you showed is part also of Heisenberg, very broad general formulation of nonlinear theory. I corresponded with Heisenberg precisely on this when I was at Boston University.
Now, I still haven't said the final thing. I wanted to do one. So all of this is calculations based on this idea of taking a specific example of potential. And so in the case that David and I are considering, we wanted to take a potential that was periodic. So just a sinusoidal potential, and then describe classical motion in interacting with a sinusoidal potential. And so that just involves inserting that into the Hamilton-Jacobi equation, and then basically solving, first of all, for the Hamilton-Jacobi, and then solving for the continuity equation. And when you do that, you discover there are two modes in classical mechanics. One is where the particle, this is always describing just a single particle. So if you describe that single particle, but your knowledge of where it's located is uncertain, then there are two cases you have to consider. If the particle has only a small amount of energy, then it cannot, it's forbidden to move outside the potential. But if it has a sufficient energy, then it'll move across the potential. So this is different in quantum mechanics. In quantum mechanics, you have things like tunneling and so forth.
Yes, yes, it is.
Right, but in classical mechanics, tunneling is forbidden. This doesn't happen, but the mathematics still remains almost exactly the same. So let's see, I'll go all through this. Let me just get to the point where I did an actual calculation. It's just showing things like that the density is conserved and that sort of thing. Yes, okay. And an important thing also is that in classical mechanics, the Hamilton-Jacobi equation is not single valued. It's not necessarily single valued. So that means that a single Hamilton-Jacobi equation can describe more than one type of motion. And the usual sort of thing in a harmonic kind of potential, or in a potential like this, you have motion that is particles moving to the left, and you have, I shouldn't say particles, you should say worlds in which particles are moving to the left, and worlds in which the particle is moving to the right. And both of these are separate solutions to the quantum Hamilton-Jacobi equation. But when you use that to solve the density, then you get to see this kind of motion, right? That if a particle is moving to the left, every time it gets close to a higher part of the potential, the packet gets squeezed. And when it's in a lower part of the potential, the packet spreads out. So this describes the propagation of the packet in one direction or in the other. So now, if you do the same thing with something that has, this is a case where you have a sufficient energy to cross the humps, right? So there's nothing forbidden. But if you do the same thing with the energy lower, then you get, with exactly the same equations, you get a completely different motion, right? That you get things moving to the right, but then they rebound and they become things moving to the left, right? And then you rebound, and so that's the origin of the sort of harmonic motion, and it consists of two separate densities. The densities moving to the left and densities moving to the right. And so it's like one density converts into the other density, and then it shifts back and forth over time. Now, the reason why I wanted to point out this picture is that to understand what's going on here is because you think this is just a single particle. So what does this density mean, right? If we wanted to ascribe some kind of physical meaning to this density, then we have a bit of a problem. So the things that happened, like back in the 1900s, Gibbs and Boltzmann came up with the idea that what you need to think of is an ensemble. Like, so you don't just think of a single particle, you think of a single particle, but in many different possible micro states, like say that same particle, but starting in a slightly different position. So you only know its starting position within a certain sort of curve. And what you're calculating is how that curve changes over time. And the thing about classical mechanics was that the members of the ensemble are completely independent of each other. Like once you say where a particle started, that completely determines its motion, doesn't interact with other members of the ensemble, right? But in quantum mechanics, this is where many worlds quantum mechanics comes from. And it's completely different than, it's not Everett's many world. This is many worlds quantum mechanics as done by Bill Poirier, and Poirier was a follower of Holland. And so Poirier came after Holland, but Poirier pointed out that you can represent all of these dynamics by thinking of the members of the ensemble as interacting with each other. So this, in classical mechanics, the members of the ensemble were fictional. They were just like, to understand probability, we have to think as if there are many possible worlds, and what we're describing is the collection of possible worlds. But the possible worlds don't affect each other. They just, all of them follow classical mechanics. But in quantum mechanics, you can take exactly the same picture, but you're left with the conclusion that individual members of the ensemble or individual separate worlds affect the motion of worlds nearby. And so that the whole notion of non-locality becomes explained as the dynamics of the ensemble. Right? So that there is both classical dynamics that describes the motion of the particles, and there is quantum mechanical dynamics that describes how the worlds affect each other. But this is the kind of damage that happens to our view of reality, right? Because that means that ultimately, in order to give some sense of reality to this, you have to accept that what we view as the real world is not a single thing, right? It's a consequence of many different worlds interacting with each other. And what our notions of quantum mechanics arise from the fact that we don't really know precisely which worlds we're in. Right? We don't know if we're in the world in which this happens or if we're in the world in which something else happens. We only know that within a certain probability tells us how to predict how this uncertainty will change. Right? So when we talk about deforming a charge cloud around the electron, we're talking about
we are not listening to you, Professor Professor Pesh. Professor Pesh, we are not listening to you.
When we talk about deforming the charge cloud, we're talking about affecting the way the probabilities, the densities of worlds affect nearby worlds. And that in each world, there's only a single electron, so that when the classical interaction occurs, it occurs in some one world. So it's like we hit an electron, even though we have a cloud, and the cloud evolves dynamically. What we're talking about is how the possible worlds evolve. And so when something happens, it happens in one world alone, but we don't know which world that is, right? And so that's the picture that ultimately arose out of David Bohm's views, I think, is that the best ontology, the best sort of physical reality behind David Bohm's ideas is to take the view that there are many interacting worlds, and all of these worlds are classical, but they interact according to the rules of quantum mechanics. So that's where I wanted to end up. And I have trouble applying this model to your paper. That's the problem.
Totally different approach. No, I see.
It is
a completely different approach, vice versa. The different objective. We are heading
so
for
that's
experimental verification. You have a beautiful
kind of have
theoretical model.
This is where my question mark comes in. In your title, you said David Bohm's hidden worlds, question mark. And that's where I would answer, well, maybe not, right? Maybe not, because right? Because
before discussing, I would like to at least present what we mean.
Yes.
Then perhaps we can have a discussion.
Okay, so I'll end there. And I'm sorry it took that long, but
yeah, I might just say I'm not going to really have very much to say, and I'll just point out a couple of equations in the paper, which I think are my most important contributions to it. So
okay,
you guys can have more time.
I do have a comment, however, regarding the presentation. Dr. Page, what you presented is very nice, extremely, very interesting, and connected with throughout history. And it is part of this enormous effort for to essentially to complete generally. However, keep in mind that, to my understanding, I've been exposed for the first time to your talk, that all the equations you present are beautiful models. Don't misunderstand me. I just want to clarify that they are outside the class, to my knowledge, the class of unitary equivalence of the Copenhagen interpretation of quantum mechanics. This means you have to exit from the class of unitary equivalence. The moment you exit from non-unitary, you accept non-unitary transformation, and I think there is one for your model, then keep in mind that there is an infinite number of possibilities.
I think I would strongly disagree, because all of these equations that I wrote down, except for the classical one, but the other equations represent exactly quantum mechanics as described by Schrödinger, right?
Well,
so
but
including the unitarity.
Again, the name quantum mechanics I mentioned before is kind of dangerous. I'm referring to the Copenhagen interpretation, which is, you know, the conventionally accepted quantum conventional enveloping algebra. All interactions have to be potential. Your interactions are non-derivable from the moment you mentioned Jacobi. You have to accept the external terms in Lagrange and Hamilton's equation. And please let's avoid entering the issue of nomenclature. They are non-derivable from a potential. This is the crucial point in my view, and this is typically for all non-linear interaction. This clearly clarified in Heisenberg book on non-linear extension of quantum mechanics. So the conclusion is that what you present is beautiful, absolutely beautiful. I don't think there's any connection whatsoever with our paper. Our paper is aimed at representing numbers in nuclear physics. But the point persists that, you know, you have an infinite number of alternatives, like the one that the moment you exit from that class of equivalence, you have an infinite number of possibilities, an endless number of possibilities. That is the reason why quantum mechanics has not been replaced to date with such as Bohm, why Bohm's beautiful mechanics, which I consider Bohm a founder of hadronic mechanics, why it has not been accepted.
But Bohm's mechanics are exactly the same as quantum mechanics.
Well, again,
there's no new mechanics, right? Well, people say Bohm mechanics, but all they mean is Bohm's interpretation of quantum mechanics.
Yeah, but you need equation, or you need equation. Well, it's
identical to Schrödinger.
Yeah, I'm a little bit
Schrödinger is just the wave equation that corresponds to the pair of equations that David Bohm used. So David Bohm used a pair of real equations. Schrödinger used a complex valued wave function, but they are mathematically equivalent to each other.
Well, I personally, I'm a formula man. I prefer to deal with equations, confronted with experiment. That's what. That's my primary interest. I'm not strong in epistemology or in conceptual interpretation. I'm not.
Yeah. So from my point of view, then, like if you take that point of view, then I think Bohm has nothing to do with what you're talking about.
No, Bohm is a founder, because Bohm. The main objective of hadronic mechanics is to complete in the APR sense. So you assume quantum mechanics as a foundation, solid foundation, and you complete them with interactions that are non-linear in the wave function, non-local, and generally non-derivable from a potential, precisely for all the beautiful reasons that you have indicated. So along those lines, David Bohm is a founder of hadronic mechanics, because he proposed, among many others, he with the Bohm VGA I mentioned in my talk, Bohm VGA non-local theory. He spent his life just mainly trying to pay honor to his work. But our effort, however, has been different. Our effort, the main difference, what is that among this infinite possibility of non-unitary extension, completion, or whatever generalization of quantum mechanics, we try to study only one class, the class which is axiom preserved. That's all we are interesting. But the moment you remove that condition, axiom preserving, my God, then and it is my opinion that everything that you said, even though it's just an intuition, I could be totally wrong. Everything that you said could be expressed in an axiom preserving form, provided you surmount.
But there is no contradiction with the axiom.
Yes, it can all
in
be
David Bohm's work,
in the isotopic element. All the extra
David Bohm's work.
I'm sorry?
But David Bohm's work does not contradict the axioms of quantum mechanics at all.
Yeah, but we need an explicit equation for the nonlinearity. Now at that point you lose. I have difficulty.
Yes, that is
exactly
correct.
Nonlinearity and non-locality. I need the equation. I need the equation, Dr. Page. Otherwise, you lose me.
Absolutely, yes, and that's called the quantum Hamilton-Jacobi equation.
And that is includes.
But that quantum Hamilton-Jacobi equation is built into the Schrödinger equation.
Yeah, but it's not derivable from an
actual. It's just one part of it.
So,
let me just say one thing.
Sorry, Dr. Garret. Violates it cannot be quantized according to the conventional quantization rule. It's not derivable from a variational principle. In other words, you have to you reach a point the moment you treat with concrete equation. You reach a point in which you have to admit there is a structural difference between theory, the solely admitting linear potential and local interaction, and theory which admits non-linear interaction. They are not. You cannot. I have difficulty in accepting that they have the same axioms of quantum mechanics. I'm sorry, I cannot.
Yeah, maybe what you're saying is that they're not derivable from a canonical transformation.
That's they're not.
Like,
easily derivable.
In classical, but in classical mechanics, there is a relationship between Lagrangian and Hamiltonian and Hamilton-Jacobi, and that formal relationship is described as a series of canonical transformations.
Be careful on that.
And that doesn't happen in quantum mechanics. Right?
Sorry if I interrupt you.
Quantum. Sorry.
Sorry if I interrupt you. When you use the word canonical transformation, technically it only applies for Lagrangian and Hamilton equation, that's what are called truncated Lagrangian, those with external term. So they apply to what are called reduced Jacobi equation, namely Jacobi equation, which the sole interaction are derivable from a potential. Technically, they are variationally self-adjoint. So the moment you consider the general one, you lose the notion of the canonical transformation, the non-canonical transformation connecting those equations are at the operator, not quantum. At the operator, it becomes non-unitary transformation. That is my point of this infinite class of theory, an enormous number of but the one that you indicated, they are beautiful. Those are, again, over and over again. This is a beautiful theory, a beautiful study.
But I don't see, that's where I have, my problem is I don't see the connection with David Bohm in your work, right? Like it doesn't.
My work is only not connected because there are many studies. That's I consider a plus. But in any case, every theory has to be justified on we are physicists and not mathematicians. Here we're talking about a physicist. So the theory has to be accepted on the basis of experimental verification, the capability of representing numbers. That is what there's been difficulty with the theory that you presented to date. But maybe by identifying the real axioms, maybe some hidden. Now the word hidden, maybe this can be different in the future. This theory are in continuous evolution. We are only interested in one among the infinite class of non-unitary transformation. Let me make my presentation, and then we can discuss intelligently.
Yes.
Otherwise,
Yes. Please continue.
Do you want me to take over with my presentation?
Yes, please do.
Thank you. Let me see then. let me see if I'm not sure I have I'm not sure I have the I have my I'm not sure I have my PowerPoint open in because we had this huge problem accessing enormous problem in accessing the meeting, connecting with the meeting. I'm not sure.
Take your time. It's no problem.
Thank you.
I don't think I mean, I don't have to go anywhere.
I am afraid I have, because it's not just
currently what you're sharing looks like the Zoom window itself.
Yes, yeah.
You probably want to view.
I have to open I have to open my. Just a moment, please. Just be patient.
No problem.
We had really serious problem in reaching you. And
I'm glad that you resolved the problem.
Yes,
sorry.
thank you. Yes, thank you.
I hope that my changes to the procedure didn't cause too much.
That's okay. It's part of life. Just a moment. No, this is just a moment. I have to. This is unfortunately, this has been a disaster. Okay.
No, I think it's been good. I got a chance to say my bit about quantum mechanics.
That's okay.
And in fact, I was going to mention that I probably in upcoming meetings I want to sort of continue this.
Yes, please
in some ways or another.
Please do so, because it's very interesting.
In the previous year, I've talking and thinking mostly about relativity, at least in our context. And I'd like to say a few words in the near future about how I see them both as being compatible with each other, so that how the relativity according to Oshevich can be related to many worlds. Like that's what I wanted to talk about.
But I have to click. I need the click where I can click for the to connect.
The screen.
You need to probably go up there.
Just a moment. There was down here. There was I think. No, I think I've lost the connection. I don't know.
You're there. You're
I know, but I have to access.
Yeah, minimize that screen with Zoom, maybe.
I have to. Yeah. I have to select Carl. I have to select I need a command to access the PowerPoint in the main screen.
Okay, just look for it.
It is there, but yeah, but I have to. There is a command from Zoom.
Yeah, but then you need to go back on the
That's
screen.
my point. That's exactly my point.
Right.
Saying they have to go back to the screen. This way, the commotion to connect with we disconnected the PowerPoint.
Yeah, just minimize that screen you have now, that Zoom screen.
Okay, yes.
Okay, I think it's there. No, I think it is there. It's there. Just a moment. I think it's maybe it's here.
No, this is
no.
It's right there.
No.
I think you.
Today has been
no. I think
connection
it's like
today has been a disaster.
Well, it's okay. This is not one of the best days.
No.
Profile picture.
I think we have to disconnect the meeting and reconnect.
New share.
Okay, you got it. Now I get it. Now wait. I have to select the PowerPoint. You see, I have to select this PowerPoint, and now finally has appeared in the desktop, and I think this is the desk. This is the. I think this is the. Okay, yes, finally, I apologize again. Okay, now I have to, just a moment, I have to go down. I have to go to, today, it's not been, but that's okay. And then, okay, finally, Now, can we remove, maybe put this on the side, Carla, because they take over my view of
Okay, I'll look. Let me
if I-
see. Let me see if I
see
can.
if I-
Like control and opposition.
No, let me ask them, Dr. Page, do you see my PowerPoint?
No, at the moment, I see only a small part of the Zoom window that you had up earlier.
Because I have the PowerPoint fully open on my side.
I think you probably have to stop sharing this and share
Yes,
something.
screen sharing.
That was my yes, was my
It's a new
original.
share.
Yes.
Yeah, so first of all, exit your existing share.
Yeah, you have to terminate sharing, Carla, please.
Stop share.
That's it.
And that's what
That's
we did.
good, yes.
Okay. Now I think, let me see which one of the
So this is share now.
I think this, I suppose, no, this is the PowerPoint, Carl. And then you click there, click please. See the blue is there. Okay, now it's blue.
Can you
Okay.
see anything now?
No, because you have to do sharing. This is the. You see,
Now
I see.
you got it.
You share now. Can you see?
Can you see it now?
Perfect.
Oh, perfect.
Yes,
okay.
perfect.
Okay, very well. So, okie dokie. Today, I'm sorry. Today
That was quick.
I know. We have to restart.
You seem to
I
go
lost.
directly
I
to the end.
reached the end of the.
So where do you need to go now?
I'm sorry
Where
today.
do you need to go?
Just a moment. Wait, Carl. Can you see me now? See the screen now?
Right now, I see a blank screen.
What did he say?
Again, blank screen.
Blank screen.
Again, we have to disconnect, Carl, and reconnect. Terminate
No,
sharing.
it says your screen sharing is paused.
Yeah, terminate, close it, Carla, please. Terminate the screen.
Stop share.
Okay,
Now,
Now-
that's it.
now we
That's what
see
I was
you
looking
again.
for.
now
This I was looking. Now,
now here is where the share there. So I
yes.
don't know. I think this might be a little different from the
Can-
other one because
Can
it's a
you
new
see now the
version.
main page?
Yeah,
Yes,
we see
perfect.
it.
Yes.
Okay, okay, good enough.
I think is a new version. That's why it's a little more.
Well, yes, but anyhow, so let me see if I'm. Okay, well, this is basically, I think that the top is covered. I don't know why, but because I want to discuss regarding the name of our meeting, but this is basically so this let's
Then
review.
see it,
Yeah,
you
but
know.
you see, Carla, but I need to move the swing.
Yeah, it's,
Can
Ruggero,
you
you need-
possibility to move the
To move,
swing?
yeah, we need to do
Because I
the,
don't.
so I don't know how. Oh, those windows, you need to
Yes,
put them in a
because
different.
they cover the equation I have to read.
I know, we need to put them on a
On the
different.
right-hand
Okay, yeah,
side.
the grid, thumbnail,
No, Carla, should be the command should be
okay.
take them all. That's it. That's it. That's how I can see. It's okay. I don't have to see myself, Carl. I
Did you
don't have
ask
to-
them, did you ask them if, are they there now?
Can you
Yes.
still
Yeah,
can you
we
still
see
see?
it. We see it
Yes.
perfectly.
Okay.
Yes,
Okay.
see it.
Give me
I
time.
think, no, I think this is a different version and so it's
Yeah, this
a
was
little
the
more complicated.
yeah.
It's
There's the
okay.
upgrade that we were requesting. Follow your email, Dr. Page. The Zoom upgrade. It's completely different. So that's why we are having those difficulties. Yeah. Without that upgrade, it would have been much, but that's okay. It's part of life. Okay. So the issue, the objective here is to reach a numerical representation of the experimental value regarding the nuclear magnetic moment. By quantum mechanics, I mean, not to repeat, I mean, the Copenhagen interpretation, conventional Schrödinger, Heisenberg equation, all restricted to sole, linear, local, and potential interactions. It was basic axiom is the universal enveloping associative algebra in our view. So those are the experimental data. This is the magnetic moment of the proton, magnetic moment of the neutron. And let's compute the magnetic moment for the deuteron, which is a bound state of a proton and a neutron. You get this value. The experimental value is this one. Conclusion, you look at the comparison of theory and experiment, and you get about 3% deviation in excess. The theoretical value is 3% more than what is supposed to be. This is for the deuteron, which is the simplest nucleus existing in nature. When you go to the zirconium, you have 30, 35%, and then this deviation are known as the Schmidt's limit. Those boundaries gives you the idea of the failure, if I may use the word, of quantum mechanics to predict nuclear magnetic moment. This is one, in my view, as well as in view of numerous physicists, a very strong evidence support of Einstein-Podolsky argument that quantum mechanics is not a complete theory. It's an excellent theory, but it's not complete. But it's only the beginning of the problem. And now, if you look at them, in order to achieve at least within 3% of the magnetic moment, you have to put the proton and neutron parallel to each other. And this is called a triplet coupling. Triplet coupling is known since the first year graduate students to be extremely unstable. And this way, this is on the right-hand side, you can see a picture of hand drawing, my hand drawing picture in my first paper at Harvard to emphasize it is called a gear model. It's been reproduced a number of times to show that gears, when the gears they couple, can only couple in singlet with the opposite spin. It is exactly the same thing for particles. Particles are not point as described by quantum mechanics according to Einstein, but they are extended wave packets, especially when they are composite. There's a main difference, Dr. Page, between an elementary particle, such as the electron, which you mentioned, and when it's a composite collection of particles. So there is a dramatic difference in the name of charge distribution, as well as in quantitative representation. But in any case, this is Dr. Cruz is also there's a point which I, in my long letter to you, which I don't even know if you received it, in the realization of your axioms. You see, I was at MIT, and they tried everything. They reached about over 40 potentials and tried to represent the magnetic moment and failed. And so conclusion, what is the problem? In my view, this is namely that is a fundamental mathematical problem. Is clearly the insufficiency, lack of completeness of quantum mechanics. Now let's go to a point in which Dr. Page disagreed. And this is called the Fermi-Weishaupt hypothesis. Namely, initially Fermi said that the charge distribution, again, careful, they're talking about collection of particles composing the proton and neutrons, and this is called a charge distribution. They call it this, ideally, conceptually, you can think about a sphere, a charged sphere, which is rotating. And both of them, they said that this, when the proton and neutron are under strong interaction, their shape is deformed. Now, the shape can be the wave function, it can be 10,000, not 10,000, but many different realizations. But the point is that you need to realize a deformation of something as a hope of reaching a numerical representation of the experimental data. You can see this on the Weishaupt. The expresses exactly this idea. Go to page 31, you will see it. Incidentally, assuming a proton and neutron are perfectly spherical in vacuum, they are not because they are rotating. But assuming so, that, or whatever shape it is, the deformation has to be prolate because it is in excess. And when you get this type of prolate deformation, then the magnetic moment caused by the rotating charge decreases, while in this case it increases. So in conclusion, this is my personal view, that the fundamental problem in nuclear physics is not physics, it's mathematical. Namely, we need a mathematical representation of a proton and neutron, whatever they are, as being extended, and the moment you admit an extension, automatically you admit a deformation, which is necessary to represent those numbers. By keeping in mind that quantum mechanics is strictly outside this definition, and incidentally, a number of your model, Dr. Page, they fall in this category, they remain local. They are non-linear, but still local, so they do not admit a deformation. So I do not expect to be able to represent numbers in nuclear physics.
Well, but I do think that this is an important sort of interpretational issue, is what exactly is being deformed when you talk about deformed charge distributions. Like, so, and you think of it as something, as an extended body in space.
But
quantum mechanics says it cannot possibly be.
Yeah, but that's we diverge. Yeah, but you go way up. In one of the my lecture indicated that the geometry that we use is high school, not even a first year graduate school. Namely, we represent proton and neutrons as spheroid per their action, according to their actual measurement, 10 to the minus 13 centimeter. I think 1 point something 10 to the minus 13 centimeter. They're spherical, or actually spheroids, lighter because they rotate. And we represent that actual physical shape measured in laboratory with a spheroid that we learn in high school. And now it is very dangerous, Dr. Page, if you start from there thinking about all sorts of abstract, then you abandon any hope, you exit from any hope of representing numbers. This is a very concrete, down to the ground.
So do you view, when you say you view protons, say as small spheres,
experimentally measured, we measure the radius.
But when you measure the way protons interact, I mean, if they are small spheres, their interaction is different than what quantum mechanics predicts.
That's what we are hoping. But again, you have to make.
No, but so it's as saying directly that quantum mechanics tells you that they can't be spheres. It doesn't tell you that there isn't a charge distribution, but rather it tells you.
Yeah, according to quantum mechanics, they're point. The wave function is only defined at one point. The potential is only defined at one point.
The wave function is
one point.
The wave function is a field. So it's defined.
Yeah, but we are entering into, we're talking about something outside the dimension. The dimension is what is measured in laboratory that we have to represent. So the sphere is what is the number that we measure. Now, what the idea of a wave
function.
You
mean something like the cross section, you mean?
Is the area with the highest density of the wave function. You can think in this way. Keep in mind that when you enter the wave function, it's fundamental to represent the entanglement of particle at the distance. But the wave function, which in my view is at the foundation of the entanglement, has the highest density precisely in that area of 10 to the minus 13 centimeter. But again, those are dangerous thinking that keeps you away from the representation of experimental reality. Dr. Page, this is my personal view.
But wouldn't you agree that?
Yeah.
But wouldn't you agree that from experimental reality, what we measure is something like cross section? So we don't.
No. We measure.
We don't measure a shape, right? We conduct many experiments. And we see how one particle interacts with the other and the probability of it moving one way versus moving another way. And that is summarized statistically in a statistical measure called the cross section. Right? So
but again, you exit from the objective of the objective at hand is different. Yeah, you and the beautiful argument, Dr. Page, but I don't see the connection. We measure the radius of the radius. You call it the radius of the proton and the neutron. and it turns out to be approximately spherical. What we have done is by deforming this experimentally measured quantity by half of 3%, we represent, for the first time, we achieve a representation of the nuclear magnetic moment. Everything you try to exit from those very, very ground, you risk to enter into a more epistemological aspect than the practical. But you have to admit this experimentally measured reality, namely the radius of the measure of the proton and the electron. You pass to cross section and many other beautiful ideas, but in this way you exit from the objective, and you cannot create a theory that represents all your thinking. No, that is not possible in my view. It will never be possible.
Excuse me, one question. How do you make the measure of the radio? Because you are made in one measure, I think, indirectly, because you are measuring a magnetic moment. Is that right?
Dr. Cruz, your question is very, very important and pertinent. Thank you for raising it. I'm not an experimentalist. The only thing that I know that this has been measured by scattering, namely they send the radius beam of think about in a nucleus, for instance, and then they send a beam of electrons, and then the cross section is used, but as to see the area in which they see the maximum response, in the interaction. That's what I believe that's how they. But if you look at the table, the radius of the proton and the are tabulated, and the same for the all particles, all hadrons have tabulated an experimental measure. The way they are done, honestly, I do not know. But anyhow, this is the objective is to represent. Well, you have seen our isotopic element as all the represents the actual dimension and actual shape of a proton and neutron and the density. The space, the three-space component represents this elementary high school formulation of geometry. And the fourth term represents the density, and those numbers are represented in an invariant way, namely that the same, once you get those numbers, they have to be the same under the same conditions at different time. Otherwise, you do not have, in my view, a physical.
Just one comment on the same subject. Rather than visualizing this as a deformed sphere, wouldn't it be more appropriate to think of it as a, say, deformation of a Gaussian or something like that?
Yes, of course.
So you have some Gaussian shape, and so the radius that you're talking about is the standard deviation of this Gaussian, right? It's the width of the Gaussian. Right? So of course the Gaussian is infinite, right? It tails off. It doesn't go to zero directly anywhere. But it has a characteristic width that's part of the expression for the Gaussian shape, and that sigma or characteristic width is the one that's directly associated with cross section, right? So
yes,
what you're saying in a sense is we consider a Gaussian over, say, 3 dimensions, and at least one of those dimensions, the sigma sub x is different than sigma sub y, right? And sigma sub z.
That's all. On the strong
that's maybe a more it's a more accurate picture because it's important to think that the discharge distribution is not a ball, right? It's something that is diffuse and it represents a probability density of something happening, of some collision occurring or something like that. But if we hit two balls against each other, they either hit or they don't hit, right? But if we hit two Gaussians against each other, the probability of them hitting is much higher if they're straight on. But most of the time, the Gaussians just pass straight through each other, right? It's only that sometimes when the Gaussian is passing through the other Gaussian, there will be a point-like interaction that occurs, because in that particular world in which you're in, the proton happened to be there at the same time as the proton in the other proton. But that doesn't happen all the time.
Yeah,
that just happens.
Be careful, because again, you are going far away from what we are discussing. We are discussing.
Well, but that was the point was what gets deformed. Like when you say it's deformed, it's the probability that's being deformed, right?
Okay, may I comment on the point before, please? Because you're talking about the Gaussian traversing from each other. This, I feel uneasy. We're talking about something very concrete: proton and neutrons, in which the radius has been measured, and we are studying them when they are on. Here is the point which. To make to reconnect with the research, you have to please keep in mind. We are studying them when they are under strong interaction, like in the deuteron, in the structure of the deuteron. They are under strong interaction. Now, the point that is incontrovertible in my view, you can make, but it can be done in other ways, is that whatever representation of the proton and the neutron you do, to represent the magnetic moment of the deuteron, this whatever has to be deformed, That's not Ruggero's idea. That's the idea of Enrico Fermi, Weishaupt, and many other physicists. Now, the simplest, you approach beautiful models, but they are highly complicated. And the simplest way to represent the number, the experimental number, which is the magnetic moment of the deuteron, is to represent them, the proton and neutron as they are in the measured in laboratory as a sphere with a radius to the 10 to the minus 13, plus or minus, or whatever it is. And then that's the Fermi-Weishaupt, not Ruggero, Fermi-Weishaupt idea, is that you can represent the magnetic moment of the deuteron if you admit a deformation. They specifically, Fermi specifically speak about the deformazione della carica, della distribuzione di carica. So, but you may think about Gaussian. I can make you a long list of alternatives that you can introduce. But the main point remains that you have to introduce a deformation. Otherwise, there is no known way of representing the numbers. Finally, there is a mathematical point in which I have difficulties, Dr. Page, I have difficulty in understanding your difficulties. All this, precisely this Fermi-Weishaupt has stimulated all sorts, 50 years of effort by many mathematicians. I gave you half a dozen of monographs by mathematicians on one advancement in, at least has been attempted in mathematics, namely to pass from a strictly local mathematics, is applied mathematics mostly of the past century, into mathematics that can represent objects, whatever they are, in extended, and therefore being deformable. So the interest in our study is the mathematics that because if you represent the proton neutron as points cannot be deformed. So you have to introduce a dimension, which is an old problem. This is you see, one of the first attempts at generalized quantum mechanics has been precisely to introduce a length, a universal length. That's exactly the point. This is an historical point. So this what has been tried to introduce a dimension. Now you don't like, the moment you hear dimension, I know now that Dr. Page, you immediately goes to many other concepts, but they are very abstract and of difficult realization in a way verifiable with experiments. Even though I admit they are nice. But let's keep going on, if I may, because I don't want to steal all the time. Let's review the situation for quantum mechanical formalism. You know it. Here I'm using the formalism by Dr. Garret. I apologize if I don't pronounce your last name because I'm afraid. So this basically universal enveloping algebra with element, we call them E, and then with a conventional product and the conventional unit. Then we and of course, this universal enveloping algebra of Lie algebra. In this case, we focus on the SU2 spin algebra. And so those are the very well-known Lie commutation rules. And then we look at the fundamental representation. And there is the Pauli matrices. And then let's check how this represents spin 1/2. This is these are the eigenvalue. Okay. The spin vector is capital S, which is 1/2 of the Pauli. So therefore, the third equation, the E3, it gives you plus or minus 1, which is plus or minus 1/2 for the spin, and so the square and so on. But here is the key point I want to bring to your attention. This formulation, this is where, Dr. Page, we have an honest disagreement. Again, let me clarify. All your theory are magnificent. They create what you presented. They create a great interest in me, but you see, they are not part of this theory because this theory is invariant under unitary transformation. That's a basic law of quantum mechanics. Heisenberg time evolution is a one-dimensional Lie group which characterizes a unitary transformation on a Hilbert space. So, but what is important? So your formulation cannot be considered to be part of this formalism. Dr. Page, I must disagree on this. Even though conceptually they may appear epistemologically, but that's dangerous. The moment we pass from equation to epistemology, then this may be, at least I feel uneasy. So, because those are the basic laws that I know. So another point that I have to admit that there is no degree of freedom. Let's forget about Bohm, the hidden variable, because I can see epistemology here, so names creating all sorts of problems, which are far away from what we intend to discuss. So the main point is that this formulation admits, under this law of unitary equivalence, admits no degree of freedom whatsoever, none. This means that there is no possibility of introducing any deformation or whatsoever, or any physical quantity. This is another historical objection against quantum mechanics that is incompatible with Einstein, is incompatible with the deformation theory. Points cannot be deformed. So that's basically the point. Einstein viewed the quantum mechanics local, so once it's defined at a point, there is no deformation that you can. So, but you know that our effort, our effort is to. Okay, so this is so let's go to the studies that we are doing. We're doing an isotopy of we use isomathematics. Now this has been said that this may create problems. So now I nailed down the realization to what we call regular universal iso-associative envelope. Regular means the derivable from a non-unitary transform. Keep in mind at this stage there are an infinite variety of some of which may yield your model, Dr. But first we do this is a non-unitary transform. Then we transform the elements of these elements of a Clifford algebra at this stage. So not only the elements are transformed, keeping in mind this transformation, but also there is appearance of a necessary appearance of an operator inserted in between things that which we interpret as the isotopic product, isotopic element, as the inverse of the iso unit. And so keep in mind the transformation of the. So do you get in this way the isotopic product automatically out of non-unitary transform? And sorry. So, but that's not enough. Here we enter in another area in which I have to be honest with you. I have serious difficulties in understanding your difficulty, including Dr. Cruz. not only Dr. Page, but also regarding the ISO numbers. The reason for my difficulty are numerous. Let me mention a few. First of all, it is not my opinion, the opinion of all the mathematicians who have approached this study, Professor Camformina and Nunes and Saragas and so many others. The notion of isofield is extremely well defined. It is a ring consisting, those elements are very clearly defined, given by any conventional number restricted to real, complex, or quaternion, nocturnal, all those three, multiplied by an invertible operator, generally out of matrix or function, generally outside the original ring, the original ring ordinary numbers. And then the moment you interpret that the multiplicative operator as the multiplicative unit of the theory, then which means you redefine the product accordingly in such a way that the multiplicative operator is the right and left new unit. Then the indicated ring of elements, which just we call iso number, but you can call it the potato, or you can call it any number bothers you. You can call it with different names. But the point is that rings verify all axiom of a field, and without any exception. Now, but in addition to that, I wanted to say this is my first reason I have difficulty in understanding your difficulty. The second one is the following. You see, when we start this map, call it a map, call it a lifting completion, use whatever names. I know that the names may create problems, but use whatever name you want. The key point is this, so avoiding any deviation, let's concentrate on the problem. The problem is the moment you start this process, you must necessarily apply the same mechanisms, the same lifting, completion, or whatever you're doing. You must apply it, also identical, you must apply it to the numeric field in which the theory is defined. And here you see it here with two equations. You subject you already defined the multiplicative unit before, so you know the transformation, so you apply the same transformation to numbers, you get iso numbers. You already got the iso product, and then so you get the entire formulation of which is absolutely unavoidable. It is yields one and only one structure, mathematical structure, that we have called iso field. But I have also additional uneasiness, difficulty in understanding the difficulty. Another one is the following. You see, I've seen many work done, what are called sometimes in a friendly Italian way, minestrone. Namely, no, let's do the non-unitary map only to the enveloping algebra, and that's it. Well, this is mathematically acceptable. This has been done by a number of mathematicians, because in mathematics, this is allowed. You can define your mathematical theory in any numeric field you want, no restriction. In physics, that's different, because unless you define, you have constructed here the isosociative envelope, unless you do a compatible isotopy of the base field, you do not have a physical theory. You have all sort of inconsistency from a physical viewpoint. In particular, the most serious inconsistency that this theory, in which on one side is, remember they were talking about a non-unitary image of quantum mechanics. Okay, so forget about Schrödinger and Einstein. Those are talking non-linear, non-local, and non-derivable from a potential. Okay, theory. So the moment you define this, but you define an ordinary field, then you do not preserve the same numerical value under the same conditions at different time. I still have another point, Dr. Cruz. This I would like to bring it to your attention. Do you remember this letter? I sent you a long letter, which I don't know if you receive it, but in which I try to list all possible realization of your beautiful, very interesting realization of the axiom of interaction. And be careful that in certain cases, here is a case that suppose on one side you have a non-unitary image of a theory, and on the other side you have a conventional field. In other words, you do not include the iso field. Then my point is that I could be wrong, Dr. Cruz, my God, but I feel from that you may include a solution in the equations that violate causality. This is well known in this is the very reason why in quantum mechanics angular momentum cannot have a fractional value, can only have integer value, because fractional value are admitted under non-unitary transformation, but they violate causality. And there are also other. So in conclusion, this is basically isomathematics, and is considered to be monolithic and a single. With mutually compatible parts, which can be very easily constructed in the simplest case of regular realization with via non-unitary transform.
Can I make just ask one question related to this? When we were talking earlier about measuring the radius of a proton, for example, if we make such a measurement, normally we would use a real number, right?
Yes, of course.
But your dynamics are being expressed in terms of iso numbers.
Yeah, but remember when you do this the iso eigenvalue, it turns out into a real number. Remember my last lecture. You look at iso Schrödinger equation. Hamiltonian isotopically applied on the ket. And then, so you have HT and then the ket. And then the value is the iso number, so the E at, but which is a number multiplied by the iso unit. But that is
a real number times the iso unit. That's all it is.
But then there is isotopic elements. So the iso unit and the isotopic element are cancelled. The end result is an ordinary number. That is the very reason for which we claim experimental verification of hadronic mechanics. In its absence, Dr. Page, you had a fantastic point. In the event you do not have, at the end of the equation, you do not predict numbers that can be verified, real numbers that can be verified. The theory has no there's no major physical interest in my view. Hadronic mechanics does indeed. Okay, so at this moment we have an infinite number of possible theory that we can non-unitary, okay, including everything in my view, all the beautiful theory that you indicated, Dr. Page. In my view, I could be wrong, but I think I could locate a non-unitary transform showing the Jacobi form of kind of Jacobi kind of extension of quantum. Certainly non-linear is very easy. Okay, so at this moment we enter into the objective of the paper. The objective of the paper is to introduce the deformation. Now we turned into a degree of freedom that will allow us to reach a numerical representation of the magnetic moment of the neutron. And the one that we propose, this is my work when in 1998, when I provided the proof of the first proof of the EPR argument, that namely that the Bell's inequality does not apply on the non-linear, non-local, and non-potential interaction, and then in which case you do have a classical formulation for a system of extended particle with spin 1/2. So anyhow, this is the realization of the isotopic element specifically for this case. And now lambda, careful, lambda is a function, is a variable. Okay, it's a variable. There's a function of, it can be a function of a wave function, can be a function of many different things. Okay.
It represents a Lorentz transformation. A boost is what lambda represents. That is correct. That is correct. But we are working on a strictly three-dimensional work. This is strictly three-dimensional to make it simpler, to avoid deviation from railroad type. No, but we don't have to go to a higher dimension. That's my point in my contribution. But anyway, go ahead. I'm sorry to interrupt you.
So it's a boost like a rotation in the hyperbolic space, is that?
Yeah, that's right. I remember that picture I showed you where you're in the three-dimensional space, but you just tip the Euclidean space up.
Absolutely. You're very true. Very, very true. Yes.
So you're not really leaving three dimensions, really. You're just mixing bivectors with vectors.
Does that mean that this particular deformation that we're talking about here should be viewed more like a rotation and not like a...
Well, it should be viewed...
Not like a change of shape, but rather just a...
Yeah, the ISO unit is just defines a a Lorentz boost.
So we're not talking.
in
So we're not
four
talking
dimensions,
about
it is correct.
changing the shape of anything.
No, but let's reach the point and then we'll discuss if you don't mind.
Okay.
So let's assume, let's make this is an assumption. Now notice that the determinant of the ISO unit is 1, so that we have indeed a special unit. Incidentally, I forgot before here to indicate I'm sorry I want to bring to your attention this point here, why we cannot use why we cannot use an isotopy of the sum, because once this non-unitary transformation, which is fixed and represents, for instance, non-linearity, non-locality, whatever, once we apply to the additive unit, which is 0, becomes 0. So there is no way that we can construct via non-unitary transform a lifting or a completion also of the sum. And that is why all our study in physics, not in mathematics, in physics, are restricted to the multiplication. Okay, so the conclusion we have now, we assume this, and then remember that with the transformation of the element of the in this case are Pauli matrices. So you apply the transformation, you get to us what they've been called Pauli Santilli, number of papers, others, and we call them iso-Pauli matrices, in which basically the main idea here is to introduce a degree of freedom. A degree of freedom, not even the word deformation. I use the word deformation in my first derivation of the representation of the magnetic moment with the actual sphere. Remember, as indicated in the draft that we sent you, this is a second alternative representation of the numerical value of the magnetic moment of the deuteron by a new degree of freedom of the spin, a new degree of freedom of the spin, which however is, once you connect it to the other paper is strictly into the 3 dimensions, strictly with the sphere. And incidentally, it's in 4 dimensions, space and time, and this was using the isotopy of Lorentz, Dr. Garret, we have to discuss this. So because there is a density implied, but once you connect this work on the other, they combine beautifully. So if you were looking for Dr. Page, if I look at the deformation, you should look at the other number at the preceding paper in 1994 of the first known numerical exact representation of nuclear magnetic moment via deformation of the measured shape and dimension of protons and neutrons, very small, 1.5 percentage deformation. Back to here, so this is the idea is to introduce a new degrees of freedom. So this is lambda is a variable. This is, I'm sorry if you disagree with the word variable, I have to use it because it's a variable. Also, I'm sorry I have to use the word hidden, because it is hidden indeed in the axiom of associativity. And if you have any better word than hidden, then I'll say thank you. But then the word hidden variable were conceived and studied by David Bohm. So if I don't put David Bohm, I will be considered anti-Semitic, or I will be attacked from many. I can be so again. So we're talking about the word hidden variable. They were first discovered by David Bohm. He has been my mentor in constructing quantum mechanics. I felt kind of an ethical duty to mention and not to mention his name. I will never publish a paper in which I treat the hidden variable without jointly mention the word David Bohm. But let's go back to the point. So
it's strange because if I think of David Bohm, I almost never think of hidden variables because the idea of hidden variables was actually developed by someone else. And as far as I know, David Bohm never used the term hidden variable at all, because his point of view was nothing was hidden.
Do you remember? Check it on Wikipedia. Check it everywhere. He's remembered for the hidden variable, primarily for hidden variable, also for other theory. But you are correct. You are correct that. But they are universally recognized as being originated by David Bohm in one way or another. So it may create a serious problem for us not to mention David Bohm. But with the understanding, but the connection with David Bohm is here in the lambda. Lambda is depending on the wave function. The lambda, it can be in an integral, volume integral. So this represents this is a realization of the non-linearity and non-locality conceived, not conceived, I'm sorry, but studied by David Bohm. But here is the novelty, which we claim the novelty. This is my 1998 paper embedded in the very structure of the concept of spin. I could not go deeper than that, embedding those non-linear, non-local notion into the very notion of spin. Now, the danger that, however, that in doing so, you abandon the spin one-half. And so my major effort in my 1998 paper is to say, no, despite this enormous increase in the degree of freedom of the notion of spin, those three matrices still characterize spin one-half. And here is summarized a very long elaboration, but basically those three matrices still verify the SU2, but only in the isotopic form with the isotopic product, but the structure constant are constant. Remember, this is a non-unitary transform. Non-unitary transform will not change the structure constant. So this is and remains an SU2 is locally isomorphic. So the Lee Santilli SU2 algebra on an isofield is isomorphic to the conventional Lie algebra SU2 defined on a conventional numeric field. That's not enough, however. Then we have to go through the construction of the representation, which is started down in detail in that paper, and finally with the eigenvalue equation. Careful here with the hat. Is an asset in the preceding there was no hat, and so this was proportional to one-half equal to the conventional polymetry. Here, no, it's one-half of the isopauli. And however, when you do the isotopic eigenvalue, you get plus or minus. And here, careful here, this is isotopic square. So each element is square, and then it's applied to the isotopic element, and then you get 3. So therefore, that's indeed the spin one-half. What is important here is where Dr. Page, I doubt whether, unless you define axiomatically the structure, I doubt whether what I'm claiming will apply to your model. Namely, what I'm claiming that this generalization of the very structure, the heart of the notion of one-half spin, and therefore the very heart of proton and neutrons, the very ultimate heart. Then this generalization is invariant over time. Namely, you have the once you fix the lambda for a given condition, then for fixed lambda, then all class of equivalence of isomechanics leaves invariant this structure, preserve the value lambda numerically, which. And the reason why, because the class of equivalence is that, however, careful, again, not to do isomathematics minestrone-wise, one piece here, one the other piece. No, you got to do systematically from A to Z. Everything you do mathematically for conventional applied mathematics, you got to lift it in the new formula. But the same for here. You see, you have a non-unitary transform. You have to reformulate it according to the rule of isomathematics. It's done very easily with this simple rule multiplied by a new operator u hat, and then multiplied by square root of isotopic element, and then immediately the non-unitary transform is rewritten identically in what we call iso-unitary. Namely, this is a reconstruction of unitarity on isospace over and only over isofield. The same, this is highly nonlinear theory. Look at here, the theory becomes linear, but only on a, so if you look at the abstract viewpoint, the theory is this Lee Santilli iso SU2 spin is strictly linear, but is linear on isospace over isofield. So that's a way of reconstructing linearity on isospace over isofield. We call it isolinearity. This has been an enormous struggle to achieve this notion, because if we had generalized the Lie theory into a nonlinear form, the extraction of any physical result would have been prohibitive and extremely difficult, assuming that it had been possible. So, so this is so basically this invariant under isounitary transform has to be kept in mind for consistency. After that, the calculations are absolutely elementary. This is Dr. Garret. I apologize for don't want to mispronounce your name. I call you Dr. Garret. This is
Sobczyk.
But I have to exercise myself. Eventually, I will learn it. As you will see from his presentation, is a beautiful. Once I saw it, I didn't sleep at night, but immediately I saw the importance. Basically, by using geometric Clifford algebra terminology that he prefers and I adopt, then he has been able to factorize the iso-Pauli into the product of a conventional Pauli multiplied by a factor, which is the deformation, call it a deformation factor, call it, I think the name is, at least I'm not that much, you know, many names we could introduce, but this is what Dr. Garret introduced, the reformulation of lambda with this exponent. And then he ends up with this magnificent expression that is results. Once I saw this, I said, my God, we got a numerical representation. And indeed, you can check the rest. You can see here that this is the connection between the magnetic moment and the spin. Is through the multiplication of a quantity G, which is called the gyromagnetic factor. Now, in this case, we have a deviation. We have a 3% deviation. So the alternative, either the gyromagnetic factor is wrong, or the spin, or there is a degree of freedom, a deformation, or a change in the structure of the spin, conserving the spin 1/2. The solution which is adopted here is that the gyromagnetic, there is no known mathematical or physical procedure that could change this number. It's an experimental number, which is a gyromagnetic factor. In this case, it's 2. The solution which is adopted here is the hat and the spin. So is the spin that is different than when it is for a point particle, in going from a point particle to an extended particle characterized with this hidden variable lambda. Then you have a degree of freedom embedded in the structure of the spin, and then remember that there is a 3% deviation in excess, has to be so 1.5 per each proton and neutron. Then you do the little calculation, you expand the Dr. Garret terms, you get this expression here, and you immediately calculate the Dr. Garret factor, the exponential. From there, you compute the lambda, you end up with a numeric value of the lambda. And that is essentially the result. You have to compare it with the conventional achievement of the first achievement of the numerical representation in 3+1 dimension using the iso-Lorentz transformation, iso-Poincaré, and actually by using the isotopy of the spinorial covering of the Poincaré symmetry, because the spin is 1/2, and you cannot do what I'm telling you with the Poincaré or Lorentz. You got to go at the spinorial level. This was done in that paper on 1994. And it combines beautifully well. Ladies and gentlemen, this is the end of my point. If you don't have if you have any question, I would like to stop. But then I would like to conclude with comments on the bound state, because they are connected with the consistency of theory. Any critical question, please? Thank you for any criticism.
I have a more question, because I understand that this is a model of magnetic moment, thinking like electric charge rotating. This is the principal idea. And then in the formation of the distribution of electric charge may contribute to the change of the magnetic moment.
Correct.
Correct. Oh, okay. But I think that this is based in one idea of Ampere, that a magnetic field is produced by a moving charge.
Very, very true. Indeed, the magnetic field of a neutron is a zero charge, but has a charge structure. So but it's rotating. So the charge inside the neutron produces a magnetic field by rotating, and that's why the magnetic moment of the neutron is directly along the rotation axis. It's absolutely true what you said. A very old idea,
yes,
which are expressed in the Fermi-Weishaupt hypothesis.
This was one point that we were discussing many times with Professor Osiewicz, in the idea that in electromagnetics, we have two kinds of properties of matter. One is charge and the other is spin. And those are different. In fact, we can think about electrical current like a perturbation of rotation of spins.
Spin currents.
Yes, spin currents.
Yes.
And I think that, okay, this is a nice proposition, but this is based in the idea that then magnetic field and in the same way, spin is not real, but is only one is produced by the charge, and then the only properties of matter are charge, not a spin. No.
That is the Poincaré hypothesis of reducing everything to charge. Yes, you also, I agree fully, Dr. Cruz. Look, this is a basic basic law of quantum mechanics, that the magnetic moment is proportional to the spin through a gyromagnetic factor. And only thing that we are talking about 3% deviation from this law. And we represented in this particular paper, we represented with degrees of freedom. We call it the hidden variable. We call it deformation parameter, deformation of polymetries. There are many, many other names. It's epistemology. The equations are important. So in here with the hat, namely, we have a degrees of freedom added in the spin, while maintaining the spin value of angular momentum 1/2. And this degree of freedom essentially is a representation of the deformation of this, which has been historically called charge distribution for a composite particle, which has nothing to do with the charge. There is no charge distribution for an elementary particle. There is a charge, and then the wave packet, and there is a different, much more complex for case of an elementary particle, but we're talking about the large particle, the composite proton and neutrons. Mm-hmm. But I agree with you.
We can say that spin determines the ISO unit. That's correct, is it not? Spin completely determines the ISO unit.
Indeed. If you assume here that the magnetic moment is the conventional one, necessarily this becomes Pauli, and necessarily the unit is the conventional unit. The multiplicative, you freeze the mathematics. So by having a deviation, you automatically enlarge. But how do you represent consistently? The only way that we know, there are maybe several, and I invite, my God, I invite all others. But the way in which we know to do it simply but rigorously is via lifting the enveloping algebra, and it is beautifully represented by Clifford geometrical algebra, indeed.
Geometric algebra really gives a lot of geometric insight into the idea of ISO spin and ISO geometric algebras. I think this needs to be developed much more. Well, I think it has been in your mathematics mechanics. There are lots of papers on all kinds of ISO differential geometry, ISO whatever.
There is also the paper we quote on the isotopy of Clifford algebra with very important application of quark theory. they quote my paper many years ago in which I prove under isotopy you reach a strict confinement of quarks. I don't believe that quarks are confined, can be confined according to quantum mechanics because of uncertainty and many other reasons. But if you do isotopy, you have an incoherence of internal and external Hilbert space, and then you have absolutely rigorous confinement with an identical null probability of tunnel effect that the Hilbert spaces are incoherent.
Yeah, I don't think you're really changing quantum mechanics. You're just changing enlarging the concept of a unitary transformation to an iso-unitary transformation. But there's no real change in, as you say, the axioms are the same.
Axioms are identical by conception and realization.
So you're just extending the idea.
Otherwise, we enter. Otherwise, we enter into this. Once we had, without a guide, we'll enter in this infinite possibility of non-unitary theory, which I indicated to Dr. Page, and then we have no guidance. I have no restriction. I feel uneasy. In this way, we are frozen. Those are the axioms. Those are the enveloping algebra. That's it. Let's see what it can do. And but we are sure that we have a causal theory. We're sure that we have numbers that we can verify with experiments, and so on. I would like to bring here see to the attention of Dr. Page. Here you can see how this is an isotopic quantity, but it's isotopically multiplied by the isostate. In between there is the isotopic element. So the iso unity, which is included in here, and the isotopic element, they cancel out, and you reach a physical numbers. That is why hadronic mechanics admit consistent representation. Unless there are, because Dr. Garret, I want to terminate as soon in a few seconds if possible, because your presentation is very interesting. Let me review this. I made the composition yesterday, and my wife Carla helped me to put them. So you have to imagine a plane here. You have to imagine a plane. Those are the only bound state permitted by quantum mechanics. This is the singlet with opposing spin. That's stable. And this is called triplet, which is unstable, as I indicated before. Because remember, this is the charge distribution, which is measured experimentally. But one of this particle, the wave function of that particle, extends up to infinity, because can verify the EPR and the particle entanglement at distance, astronomical distance. So this is just for the highest the density concentration. But anyhow, the part which is measured. So, but this will give you spin 0, and in any case will be so far away from the magnetic moment. So the only way to approach the magnetic moment to use this, but this is inconsistent. So this is totally extremely unstable. So that's why this Dr. Cruz. These are some of the implications of inconsistencies of the realization of your beautiful, which I consider very nice axiom of the notion of interaction. But you have to be careful to if you restrict only the entire description to potential interaction or potential linear local and potential interaction, you have unbelievable situation in which I left MIT. I left MIT because I could not accept this description of the deuteron. And I went to Harvard. I felt I respected all my colleagues, and we remained very good friends at the time. But I couldn't remain. It was I just could not accept the deviation of quantum mechanics in nuclear physics were too much for me to accept, and that's why I went there to complete quantum mechanics. But anyhow, so if you accept isomechanics, you have additional. Very quickly, I want to say you have additional bond, which are prohibited in quantum mechanics. These are called the axial triplet. The proton, I'm talking about the deuteron. The top and they can couple each other through strong interaction with parallel spin. You get spin 1 immediately in this way. And the other couple, however, opposite spin, this is extremely repulsive. But this new notion has permitted us to represent the deuteron, to understand the stability of the neutron. Remember that the neutron is unstable, it decays after 15 minutes. So what appears to be the case is that that the neutron down here is decoupled into the particle of its original synthesis. Neutron is synthesized in nature by proton and electron, and appears to us as a single body of a proton and an electron. Apparently, under strong interaction, the electron is kind of pulled out by the neutron and stay in between, because it's pulled out because the electron is attracted by the positive charge of the proton on the top with an enormous Coulomb force. So in this way we understand the stability of the. We hope there are other, but I couldn't see no other. The stability of the deuteron, while the neutron is highly unstable when isolated. Not only that, but we can represent also. Notice in this case is a three. The deuteron will be a three-body structure, and here there are two additional works on for the reconstruction of the exact representation of the deuteron magnetic moment, but in this case as a three-body system. Remember that what we studied was a two-body approximation, okay, but not in the reality we believe that it's a three-body because the spin is one, so it indicates you that it's three. And then the deuteron is very easily but then once you view this idea, then it's very easy to. That's why our study of nuclear fusions are based on this conception of a bond of proton and neutrons. But to achieve anything practical, we have to develop a new species of chemical species, which we call magnitude, because we have to expose the nuclei. Nuclei are extremely protected by the electron clouds. Unless you expose the nuclei, don't dream of achieving nuclear fusion in any appreciable amount. But that's not enough. Then the spin had to be coupled properly, and you see the spin are coupled in this way, and so on. So this has been our basically. You should know that those studies which appear so essentially in reality they could be, if seeded in a constructive scientific environment and receptive and supportive scientific environment, can open up basically new avenue. See, this is ready for the fusion of those two nuclei. You need what we call a trigger, an explosion or something that pushes the nuclei together. The moment they are in touch with each other, then strong nuclear forces are activated, and the fusion is unavoidable. So basically, this is what keep it in mind that there's not only the study of scientific curiosity, but there is what is background. This effort, I only hope that one day we scientists in America, we go back to an orderly, to return to what the scientific democracy used to be, because I have to compare, the investment, hundreds of millions of dollars for the hypothetical search of dark matter and dark energy, by keeping in mind that Einstein, Hubble, Hoyle, Fermi, de Broglie, and many other scientists died without accepting the expansion of the universe. So we spend hundreds of millions of dollars, something hypothetical, opposed by the masters. But that's okay. I will not object. But then when you talk about new form of energy that we are desperately needed, then oh no, that is an anomalous measure. No. Then that is an imbalance that I have to confess you. I have to, as an American citizen who really care about our country, that really worries me. In this winter, hundreds of beautiful fellow Americans died for tornadoes in winters. What will be in 4 or 5 years? Will be a multiple of that number. What will be after that? Why those enormous society that eventually will become political, hopefully not the military disruption in our beautiful country. What's the origin? Lack of new clean energy, lack of new clean and nuclear fusion, another clean form of energy. They cannot, in my view, have been unable to We haven't been unable to achieve them with quantum mechanics. Let's at least try them. Let's keep trying. Let's keep investing billions on the conventional search for the controlled fusion. But at the same time, let's search for our very survival until there is time. Let's look for alternatives. So I want to conclude with I want to conclude with the certainty that America has a great vitality. That's the reason why I'm an American. And I'm certain that America will eventually come back to its senses for an equitable and implementation of scientific democracy. Dr. Page, that is the reason why I'm so interested in this series, because you imposed this series on the ground of scientific democracy, that everybody of us can express our idea without any pretension or expectation to be accepted, but at least we have the freedom of acceptance. It is a beautiful idea that I'm sure, I pray, will be propagated throughout the entire American environment. Thank you.
Okay. I think we're much past our normal closing time. So of course I have many comments that I would like to make, but I think I'd reserve them for future meetings. So just before closing today, I wonder if anybody would like to reflect on sort of the nature of future meetings or the frequency of our future meetings. Should we continue as we had last fall, or should we deviate in some way?
Dr. Garret should have his meeting. Definitely, I would recommend maybe have discussions. I will be very grateful, Dr. Page. I have additional criticism. I'm very interested in.
Yeah, I would just like to emphasize the geometric aspects, which I think up till now have not been sufficiently examined.
And it is
contribute to the theory.
Could we perhaps agree that you could continue, Dr. Sobczyk, with the presentation on this subject or a similar subject, but with more emphasis on geometric algebra?
I like to just to introduce the idea of an isogeometric algebra and show you how clearly the ideas involved with, for example, this idea of a passive Lorentz transformation is at the heart of this idea that is exponed, that Professor Santilli has been talking about.
Okay, perhaps could we continue that next week?
Yeah, that's fine.
That'd be great.
Yes, but I would suggest that because we have not yet reformulated with the geometric algebra the isotopy of Lorentz and Poincaré. So I don't know whether we can do it anything in time for the next meeting. But
at least
maybe we can just continue this meeting next week, because we're just discuss all the ideas around this then.
Yes,
I believe that would be a good idea.
And any quick criticism, Dr. Page, please. I'm very grateful for any. Will help me to understand the limitation of our description of our assumption.
Yes, I think my main criticism is really directed on the specific model that you employ when you discuss things like deformation and interaction between extended bodies. My problem is initiated, I guess, with the notion of extension, and if that extension is necessarily extension in space. By that I mean, from the point of view of the work of Olszewicz, we could say that relativity is determined by the relationship between time-like vectors, and that there is a natural factorization of the algebra that separates time from space. But it's a presumption that if we separate space-time into time and space, that the only thing we get is space, right? So relativity starts with the notion of understanding time, so the relativity of time, and with that we can say what goes beyond time, and the most natural thing that goes beyond time is spatial extension. But I don't think that there's any sense in which we are limited to having only two independent variables, or like, so that we don't necessarily have, if we don't have time, then we necessarily have space, is an assumption that we made. So, which is in addition to that that's required for relativity. So my proposal basically would be that there is such a thing as extension in a quantum mechanical sense, which does not involve extension in space. So that we still have the notion of point particles interacting like points, but these particles are not extended in space as such. They're extended over a different independent variable, not time, not space, but another independent variable in which we use to describe the extension.
Yeah, I'd like to just comment on something related to that. Is there a separate idea of the quantum mechanics of time from the quantum mechanics of space? Can you separate the two ideas?
Yes, absolutely. There's very, very specific differences between the way time is treated in quantum mechanics versus the way space is treated in quantum mechanics.
I'm wondering if you could introduce quantum mechanics of time to generalize that to include space without just by talking about quantum mechanics and time.
There have been attempts to do that.
Yes.
But most of them are only really of theoretical interest. My direction is going from an Eulerian description to a Lagrangian description, basically, so that accepting the idea that quantum mechanics has something to do with fluids, but that an Eulerian description may not fully describe what's going on, or at least it makes the dynamics look complicated compared to a Lagrangian description, where we can specifically introduce a new independent variable with which we use to basically label worlds. Like, that's why we need to accept this idea of mini worlds, so that a particle is extended not in space but across many possible worlds in some physical sense. So it's still geometric in that sense, but it's not limited to time and space. Like that's
beautiful. This is a beautiful idea. The point that you mentioned on the page before, the deformation of a Gaussian, this is beautiful. It's a very, I think, and we could reformulate everything I said via the Gaussian and change the Gaussian.
But
yes.
the critical thing is to avoid thinking of it as extension in space, because as soon as you start to think of it as an extension in space and you make pictures of solid objects, then this interferes with the facts that we know it as far as quantum mechanics is concerned.
Yeah, but it is an abstraction that the experimentalists will.
I understand that that's a model.
It's just,
but I think
it's a representation. No, it's not a model. It's not only a model. It's a representation of an experimental reality, a measurement of the radius. Now, the interpretation of that sphere, there is many different interpretations. You mentioned only a few. However, they have to admit the reality of the actual size, admitted by all physicists. That's the mainstream, not Ruggero saying so. No,
but size is something that is, I think Jesus mentioned this, that size is something that you impute using other measurements, right? You don't have a ruler with which to measure the size of a proton. What you have is a whole bunch of experiments that show how electrons and protons interact in a high energy situation, right? And so you have probabilities and cross sections and so forth, which you then impute the size.
Yeah, but you can do abstraction up to a point. Then you have enormous difficulty to apply to represent number. But there are, for instance,
the point is a little bit different, and this is what Oshevich insisted many times over and over again, is that experimentation is conditioned by theory, right? So that,
very true. Very
theory
true.
comes first, right? First you have a theory, and then you make a measurement. Yeah. And what you're doing is you're using the measurement to calibrate your theory. So
Yes.
so
Well,
if your
we have,
theory is
we
that
have, no,
so you
careful.
see, so if your theory is that something has a size, then
No,
you'll use your experiments to determine that size.
No,
But
no.
it's a mistake to think that the size is something real, right? That's
Well, it is one of the aspect of a very complex reality. And if you speak to, you should speak with an experimental nuclear physicist about this issue. For instance, now we know the density of a proton or neutrons. Where is that density? It's like in other words, it's a semi-classical. In other words, as a first step, you have to admit that while it is very even though it's crude and primordial, but nevertheless it's effective and it provides a representation of numerical facts that you cannot ignore. But with understanding, however, that this crude representation of where this density is, this crude representation admits a number of alternative representation, which are important, significant, provided, however, they can represent the experimental number as easy as we do. Because if they don't represent the experimental number, Dr. Page, careful, because that is
I absolutely agree that in the end you have to explain the same numbers.
Otherwise, you are doing epistemology. That's very easy to
pass.
I
understand.
Very easy to pass from real physics to epistemology, especially when theory becomes
the point that Roshevich was making is that one should not deduce. You should not be able to expect to deduce from measurements the nature of reality. The nature of reality comes from your imagination. And experiments are the way that you
measurements determine your imagination as well. It's a two-way street. You can't eliminate one from the other.
No, please. Let's the things that I can follow you up to a point. There are certain basic numbers in nature that there is no theory whatsoever that can predict. The mass of an electron, the electric field of an electron, the mass of a proton. There exists no theory that can predict it while representing all the characteristics of the classification model and so on. So there are certain basic things. So we do have indeed a theory consistent, totally self-consistent, that represents the sphere, the shape and the density of the proton and the neutron. Regarding the deformation, there exists an infinite number of possibilities depending on the number of the nucleus and so on. This has to be derived from the experiment. So the thinking that since we cannot derive the deformation from the theory is an insufficiency of the theory, I disagree, Dr. Page, strongly and in an irreconcilable way, because there is a mixture of misinterpretation here. There is an infinite variety of possible deformation depending on
for example,
theory and
I know
measurement go hand in hand. You can't eliminate one without the other. You need both of them.
Exactly. You need both. In other words, you cannot do only abstract. I discussed this with Professor Zevich at length. He knows everything. He knew about
Noshevich never. Definitely. Noshevich never promoted the idea that you could do physics without experiment. That's not. That's a great
mistake.
overstatement.
That was Aristotle's mistake. He tried to do just theory and lost experiment entirely. That limited Aristotle.
But the point was that fundamental ideas don't come from experiment. Fundamental ideas come from theory. Right? So if we say
what comes first, the chicken or the egg? I don't think it makes sense to say one comes before the other. The chicken or the egg.
The thing is,
mathematics come from the idea and not from the experiment. But at the same time, the same physical event can be interpreted in a number of ways. If you have a model that represents for the first time experimental results, you cannot say, "Oh no, I don't like it because I have a better one." Sure, you have a better one, but becomes isonitarily whatever model you work out in the representation of the magnetic moment of the neutron, we can prove that it is iso-unitarily equivalent to the model I present today, and the one in space-time, which is 1994. So you're talking about an alternative formulation, which is very welcome and solicited and invited. But you cannot say that this is wrong because I don't like the representation of the proton as a sphere.
No.
Say that.
Just to quote Eshevich one more time, everyone has the right to be right. That's not one person who is right and another that's wrong.
Everyone has a right to be wrong too.
Well,
Professor Osiewicz knew
the counterexample, yes, the counter to that, of course, is that everybody's wrong in a little way.
Yeah.
Professor because we're just dealing with models. No model is perfect.
Yes, no model is perfect. No model can represent everything and satisfy everybody. No, Professor Osiewicz knew about not Ruggero's. This is not the Ruggero's idea. Here we just there's an idea of Fermi and Weishaupt of the formation of the charge distribution. It's their idea. We just presented we just show the plausibility of the idea. No, that's the only. But Dr. Pate, it remains not Ruggero's idea or Dr. Garret. It remains Fermi, Weishaupt idea. Let's deform those charge distribution even slightly, and we get the exact representation, and we prove that in 2 papers, actually in 4 papers. 2 papers for the deuteron as a 2-body, and 2 additional papers for the deuteron as a 3-body.
It has a lot of the same characteristics the criticisms that people make, for example, of the standard model, is that it's a purely phenomenological theory, that it has enough parameters that you can fit what you want because it has enough things to tweak, right? And I'm a little bit concerned that the iso-mathematic ideas is a bit in that direction, right? Because in a sense it's perhaps too powerful, right? That you have too many options, and in fact it would be surprising if you couldn't make it work, right? Because it has so many options that there must be a way to make it work.
Well,
right?
again, I have to disagree. You didn't in the isomathematics characterized by one object and one object only, the isotopic element, or if you want, the iso unit, and that represents the physical characteristics of nature, at least an approximation, that cannot be represented with Hamiltonian.
Namely, spin. Represents spin.
That's only the sphere and density, the shape and density, and the nonlinear, non-local, and non-potential interaction. That is all. But so because then you can apply exactly the same concept to what you have shown today. You can show today you can easily you add an extra term, a nonlinear term, and it represents the supernova explosion and so on. You can apply exactly the same thinking to virtually all theory. But it happens that isomathematics is very frozen. We have one isotopic element.
But this, well, in the particular case that I was talking about today of the classical wave equation, one isn't free to add just any arbitrary nonlinear term.
Yeah, but then you don't represent.
One needs to, the term that you need to add is determined exactly by the theory.
Yeah, but
not by experiment.
Which experimental number you represent? What is the experimental reality that you represent?
Classical mechanics, right?
No. We're talking about particle physics. What can you represent in particle physics? I know no representation of what you,
I think that for example, in the formulation of Heisenberg of quantum mechanics, he started with the spectral lines of emission of the atom, and then with the base of these experimental facts, he proposed his theory.
Yeah, experiment came first in this case.
Yes, experimental came first, and Heisenberg theory explained exactly.
That's what we have done in the paper. That's what we've done. The experimental numbers have come first. We have tried to represent them for the first time.
Yeah.
So let's continue this next week. We've been going a long
Absolutely,
time.
yes.
Okay.
Very
Okay.
well.
Okay.
This will be the entire
Yeah.
session will be yours, Dr. Garret. Yes, indeed.
Yeah, that's right.
Okay.
There's no room for me today.
But the next
Okay.
next session will be entirely
So,
yours. Okay.
It was very nice to meet everyone again, in this new year, and I look forward to talking again next week.
Very
Don't
well.
get Omicron.
Okay,
Don't
very
get
well.
Omicron.
No,
It's
no.
nice to see you again.
Stay well.
Everybody.
Very well. Thank you. Happy
All
New
right.
Year to everybody.
Happy New
Okay.
Year. That's right.
Yes,
Good
indeed.
day.
Bye bye. We'll
Bye.